Oh, hi everyone. Thanks so much for showing up for your math learning. I'm Mr. Jennings Prime. Mr. Jennings is very sorry he couldn't join you today. He couldn't bring himself to face you all because he told you very clearly that you would be getting your test back on Tuesday, and he's not finished. So he wasn't able to come to school today out of embarrassment, so you have to deal with me. Okay, I'm Mr. Jennings Prime. So today we are looking at taking our mx plus b and dividing it by another mx plus b. I heard y'all like linear relations so much, I put a linear relation under your linear relation. All right, so let's take a look. We're going to skip over that. We're just going to get going. Our goal is to be able to graph these things, apply our algebra tools to these things, and also look at the graphs of them and build their equations. So you want to be able to go from graphs to equations and go from equations to graphs. If you have those two skills, you are good. All right, so let's compare these. If we have this function, f of x is equal to 7 over 2x minus 1, that's something we've looked at before. What's the difference between f of x and g of x? Yeah.
G of x is basically f of x just shifted out by 2.
Yeah, we just have a vertical translation by 2. We just shifted up by 2. Add 2 to every output. It's a C transformation, a vertical translation from grade 11. So that's all that is. Okay. Now let's take a look at these ones. We already know that if this is f of x, is this, and this is g of x. What do you think? Why is there this like other one, h of x, that looks totally different from the other two over here? What's the relationship between f of x, g of x, and h of x? Nathan?
I think the second and third ones are supposed to be the same.
Do you think, are you trying to tell me that these things that look totally different are actually the same? Does that make any sense? They can look totally different but be exactly the same? Well, let's test it. One thing we could do is we could actually do this addition, right? So how do we add an integer to a fraction? Let's do it up here.
You get the same denominator.
We have to create a common denominator. So I get out my create common denominator pen. I multiply by the denominator upstairs, and I multiply by the denominator downstairs. So I've basically taken 2 over 1 and multiplied it by 1. So that gives us this new line where we know g of x is equal to 7 plus 2 times 2x is 4x. 2 times minus 1 is minus 2. We'll put that in brackets, even though it doesn't make a difference, all over the now common denominator. Does that make sense, that next line? Oh, would you look at that? That function could have also been written algebraically totally the same thing as 4x plus 5 over 2x minus 1. And the cool thing is, everyone, that's our topic for today. So we can write these functions in this way where we're including that transformation, but we would consider this form here, polynomial over a polynomial, to be the fully simplified form. That's like our standard form. Okay? So let's keep going. All right, so we now know g of x is equal to h of x. They're not transformations of one another. They are absolutely algebraically equivalent. Okay, let's keep going. So rational functions have a linear, these ones have a linear numerator and a linear denominator. Tomorrow, the lesson is any order. So we could be quartic, we could be cubic, we could be sextic, divided by any order. So we're going to up the complexity again tomorrow, all right? And these just end up looking like linear reciprocal functions, okay? They're going to look very similar. We know these have like this shape. This is 1 over x and 1 over x. It looks like this, right? It has that asymptotic behavior. A single horizontal asymptote, a single vertical asymptote. These ones are just going to shift it somehow and stretch it so they might look like this, right? They might look like that. You know, the asymptote shifted up here and over there, whatever. We're going to investigate that stuff and learn about that stuff. So let's figure out where these things have their asymptotes. Vertical asymptotes. Where would I go looking for a vertical asymptote of a function like this? What is it that creates that accelerate up to infinity or down to negative infinity behavior? Which part of it, the numerator or the denominator? The root of the denominator is very well said. Yes. So if there is a value down here which makes the denominator equal to 0, we would know that x cannot be that value. Why? He's going to say the pizza thing again. Yeah, you can't divide by 0, folks. It's just not allowed. It's not allowed by logic. It's not like people got together and said, hey, how about we not let students divide by 0? No, no one did that. The way math works does that. It's like saying, how long will it take 0 goats to eat all that grass? See, I didn't use pizza this time, right? 2 goats will eat it twice as fast as 1 goat. So will 0 goats eat it 2 times slower? No, it's infinitely slower. It's 0. It doesn't work. It breaks down. It's not 0. Okay, so if that equals 0. So our vertical asymptote is where cx plus d equals 0. So then we have cx equals negative d, and x equals negative d on c. That's where it is. That's where your your vertical asymptote is. The horizontal asymptote, gee, I wonder where that's going to be. Should we take a look at some examples? Should we take a look in Desmos, my favorite place? Let's go ahead and look in Desmos. Okay. Oh, you got an idea?
Maybe like A over C or something.
Oh, well, why do you have such a questioning look on your face when you say something that's so obviously true?
Oh, it is true?
Yeah,
Oh, okay.
that's really good. So do you want to share your insight with the rest of the class and then have them puzzle it through why that makes sense? What did you notice, Nathan, that led you to that?
Well, I noticed that the way we got the 2 into the top of the fraction was by multiplying it against the...
Yeah. Cool. So in grade 11, this horizontal asymptote would have been like we would have had 1 over k x minus d plus c. This was our horizontal asymptote, right? Like that integer part that comes out if we actually do the division. Okay? Another way of thinking about this, our horizontal asymptote is just a over c, and you could see if you did the long division, that's what you would get as your constant that would come out. Okay? Or, here's the other way to imagine it. As x approaches positive infinity, this part of your function totally overwhelms that part. This never grows, your b and d. They're not influenced by your x. If I have like ax plus b, let's look at one, 2x plus 3 over 3x minus 17. Okay? In the beginning, that has like when x is close to 0, this has all kinds of wild values. But as x approaches infinity, like let's let x just be 1,000 here. All right? We have 2,003 divided by a little bit less than 3,000. We're extremely close to 2/3. Now let x be 1,000,000. You've got 2,000,003. Notice that the 3 is basically irrelevant at this point. Over 3,000,000 less 17. Notice that the less 17 is basically irrelevant. So you can think your way through this by practicing that. I am going to extend to infinity this problem. Yeah? And so this is like the same type of thing you can do. It's called a reductio ad absurdum. It's a logical, it's a logic strategy that you can use to undermine someone's argument. Like if Nathan says, I never do laundry. You can be like, well, what about in this really extreme case? You're on a desert island and all your clothes are dirty and the only piece of civilization you have there is a washer dryer. Like, you're not going to use it? You're really not going to use it then, Nathan? You're not going to clean your own clothes? Like, we can find the time. We can find go to the extreme. So anyway, go to the extreme with this and you'll see this is where you get your horizontal asymptote, A over C. Okay? So does that gives you where your vertical asymptote and where your horizontal asymptote comes from. Make sense? Do you do your laundry or does a parent do it for you?
Do my laundry.
You do your own laundry?
Why is that so
Good for you. Well, it's good practice because when you go away to university, It took me 6 months until I was like, okay, I better do my laundry.
Oh, dear.
Yeah, it was not good. It was not good. But that's a story for the real Mr. Jennings to talk to you about when I get back.
6 months.
It's a little bit of an exaggeration.
I was really hoping.
I thought you said 6 weeks.
That's closer to the truth.
Still a little insane, but.
Yeah. Okay, now let's talk about our key points. Key points here are just our X and Y intercepts. So, x-intercepts occur where f of x equals 0, and y-intercepts occur where x equals 0. So let's try both, okay? If we have f of x is equal to 0, but I also know that that's ax plus b over cx plus d, how would I find the value of x that makes this true? How do I find my... Wait, am I finding a y-intercept or an x-intercept here? I am finding an x-intercept because the value of my function is 0. The value of y is 0 all along the x-axis. So if you're hearing all along the watchtower in your head and you got Jimmy going, all along the x-axis, the value of y is 0. Then that will help you remember. That's how you find x-intercepts. You set the function equal to 0. You're just setting it to be on the x-axis. It's very straightforward if you're thinking about what x means and what y means. Okay, so let's keep going. How will I find the value of x that makes that true? Dax, do you know?
To find what?
To find what value of x makes this true? It's the root of...
The denominator?
No. That gave us the vertical asymptote, which was very well given by you before, because that's what creates that crazy divide by 0 behavior.
Yeah.
But here we're just crossing the x-axis. We're allowed to do that, and that will happen when the numerator is equal to 0. So if the numerator up here, this part, is ever equal to 0, then the function equals 0. That's the only way to do it. Okay? So that's the way you create an x-intercept. All right? Because we're linear over linear, there will be 1. Unless we happen to have a hole there. We'll talk about holes later. I don't think we get to talk about holes today. So in this case, you can algebraically do that by multiply both sides by the denominator pen and multiply both sides by cx plus d. But that's kind of a ridiculous move because we're just multiplying 0 times cx plus d. And anything times 0 is 0, so this just goes away and stays 0. This cancels, and you get what we talked about. So, if we have ax plus b equals 0, then that means x equals negative b on a. That is always our x-intercept. Spelling is not my forte right now. Now, that is set f of x equal to 0. That's where we get x-intercepts. Let's find some y-intercepts. Okay? You just set f at 0. You set the function equal to 0. That's going to equal a times 0 plus b over c times 0 plus d. Gone. Gone. There. B on d is your y-intercept. And so your x-intercept, properly that would be negative b on a, 0, because the y value is 0, because we set it so. Okay? And then your y-intercept would be 0, because we set it so, b on d. Okay, cool. All right. Ready to put the tire on the road and do some examples together? Tell me, yes, Mr. Jennings Prime. You are taking too long with your too many anecdotes, and we don't need to hear you sing Jimmy anymore. Okay, let's go. All right, I'm starting to lose Hayden, so I better keep up. All right, here we go. F of x equals x minus 2 over x minus 4. Let's find our key points, check our asymptotes, and state the domain and range. Okay, I'm going to do key points first because you can do this in any order. All right, so F at, I'll race you. Find the key points. So I happen to know that this point 0, 1/2 is my y-intercept. And now I set f at x equal to 0, and that would be equal to x minus 2 over x minus 4. Go ahead and multiply both sides by x minus 4, and I get 0 equals x minus 2. X equals 2. Look at how fast I am. Can you beat me? Can you be faster than me? No, that's fine. You'll catch up. How much practice have I had with this stuff? I've had a fair bit. So you want to get this much practice. You want to be a little angry that I'm fast at this stuff and you're slow and need the whole period for yesterday's quiz. You want to be a little angry. And you can direct your anger at me. That's fine. You're like, Mr. Jennings and his fast math. I'm going to show him by getting faster, by practicing. So practice a lot. That's the only reason I'm fast at this stuff. Okay, so I have this point 2, 0. So I've got my key points, my x and my y-intercept. Now I test my asymptotic behavior, but I need to find my asymptotes. My vertical asymptote is given by the whole. It's given by x equals 4, okay? That's my vertical asymptote, because that would make that equal to 0. So I found it. So I can test my behavior around 4 and find out what this function does. Okay? My horizontal asymptote, what's my horizontal asymptote here? As x approaches infinity in either direction, what does this function take the value of or approach the value of? 1. Because the ratio of our coefficients here is 1 to 1. So our horizontal asymptote is that y is equal to 1. So I see that I'm working with a half here. So I'm going to set my asymptotes with my setting asymptotes pen. And I'm going to say 1 is up here at 4. Okay, that's my scale for 1. That's the line y equals 1. Okay, and then my vertical asymptote is that x is equal to 4. I'm going to put that at 2. So 1, 2, 3, 4, 5, 6, 7, 8. There's x is equal to 4. So I just changed the scale to suit my mood and to allow me to demonstrate what this looks like. This is x equal to 4 because I say so. Okay? Now, as x approaches infinity, f of x, I just go ahead and test it, and I can test this somewhere else. This is rough work when you test. As x approaches infinity, f of x, I'm just going to look at f at 1,000. This is equal to 1,000 minus 2 over 1,000 minus 4. Okay, that's equal to 998 over 996. Am I above 1 or below 1 there? Am I bigger than 1 or smaller than 1? Bigger than 1. Oh, that's interesting. This is a little different than the reciprocal functions we looked at last week. They approached 0. So we were talking about approaching 0 from the positive side and approaching 0 from the negative side, and the values we were getting were positive or negative. Here they're just bigger or smaller than 1. Okay? They're both positive. All right? So some people will get confused by them like both being positive. So I approach, f of x approaches 1 from the positive side. And as x goes to negative infinity, we know that this is going to be approaching 1 from the negative side, but we could test it by doing this. Swap the signs there in your rough work, and then we get here negative 1,002 over negative 1,004. That still cancels, right? We still get positive. Am I above 1 or below 1? I am now below 1, so I verify it by doing this test. Okay, so I have f of x approaches 1 from the negative side. And then as x approaches 4 from the positive side, we might test that out this way. F at 4.001 equals 4.001 minus 2 over 4.001 minus 4. We are here. 2.001 divided by 0.001. That's number divided by extremely small number. Is that approaching positive infinity or negative infinity?
Positive.
Positive infinity. Do I need a calculator to show me exactly what value that is? No, it's just a test to show me this is way up towards positive infinity. So as x approaches 4 from the positive side, we are getting positive infinity. F of x is approaching positive infinity. And then process of, I don't have the patience to show you the other one, but you can absolutely do the other test if you want. Okay, fine, I just swapped the direction. I should show you. Okay, fine, I do have the patience for it, but I'm only doing it because you made me. You made me do it. Okay, so I test. I say 3.999 minus 2 over 3.999 minus 4. And then I get, instead of 2.001, I get 1.999, which is infinitely close to that. And then down here I get, you see I get a little negative number. Is that now approaching positive infinity or negative infinity?
Negative.
I got positive divided by negative. This is absolutely negative. Pat on the back, everybody. So now we know our asymptotic behavior and we know our key points. We know the equations of our asymptotes. We are now ready to create a great sketch. If you want to make an even better sketch, I have there 4. This is x is 3. That's x is 2. That's x is 1. I could test a few points and get really accurate. So I go ahead and put 2 in there. Oh, I already know that x is 2. I have a key point, so I better graph that. Let's go ahead and graph it now. This is one of my key points. X is 2, y is 0. X is 0, y is 1/2, so that was there. And then I'm just going to go ahead and approach my asymptote in that direction, like my asymptotic behavior said I should. And then I'm going to arc through there and make it symmetrical as much as I can and go down that way. This is going to be a symmetrical reflection of it on that side, going this way and that way, like that. There's our function, roughly. If you want a better sketch, test some points and put in the points. But you absolutely need to demonstrate that asymptotic behavior with your sketches. That's the real key part there. Okay? I thought I have this example for you to try as well. Do you have anything you still need to copy down there? Any questions before we move on? Move on. Let's go. Okay. Yep.
Do we factor on this one?
This one? Yeah, you could factor if you want. You don't have to, but you could. Once we get any order over any order, factoring is going to be a major part of our strategy. Okay, here you could factor, but you don't need to. All right. So here, key points. Check asymptotic behavior. So first, everyone go do key points. I'm going to pause the video. You're going to find the key points, then we're going to resume. Go. Okay, we found them. And we found them to be here and here. So if you have questions about that and you want to know how to find those efficiently and quickly, grab me after the lesson and I will talk you through it. Now let's find our asymptotes and check our asymptotic behaviors. Where is our horizontal asymptote? How did you do that? Our horizontal asymptote is at y is equal to -1/4. That was very well said. I agree with you. How do you know that to be true? Yeah. It's just the ratio of these coefficients. You can imagine x get very large, or you can do the darn division. Doing the darn division is okay as well. And then you will find that that's what it is. Good. Okay. And then our vertical asymptote is equal to what?
-4.
Indeed it is. So our vertical asymptote is given by x is equal to -4. How did you do that?
Put b over a.
Oh, okay, so this one down there?
No, the top one.
The top one.
No, I did it wrong. But
Yeah.
it's still right, but
Yeah.
I'm just like it had the same ratio.
Okay, so for our vertical asymptote, we're setting the denominator equal to 0, because that's basically like state your restrictions from grade 11, right? Remember we would have to state the restrictions for these things? It can't be that. That's why it has an asymptote there. It never touches the asymptote in this case. So the vertical asymptote is x is -4, because that would make the denominator there equal to 0. -4 times -4, well, that's +16. Positive 16 minus 16 happens to be the only value of x that makes that 0. So that's why we get a unique vertical asymptote here. All right, so now we test stuff. As x approaches infinity, so we've got, okay, let's test it. F at 1,000 is equal, you can do 100, you could do 10, but I think you want to be a little bigger than that. You could do 1,000,000. It's up to you, okay? We have 1,000 minus 4 over 4,000, negative 4,000 minus 16, so we're negative 4,000 minus another 16. Okay, we are 1,004, but no, we're not. We're 9,906. Negative 996 over negative 4. Oh, no, we're not negative though. I put the negative on top. I'm talking out loud and it's bad. Over 4016. Okay, is this one bigger or smaller than our horizontal asymptote of negative 1/4? Negative 996, 1,000 minus 4, so that's 906 over negative 4,016, but I don't like writing the negative on the bottom, so I float it to the top. Yeah, it's the same. Like I could say 996 over negative 4016, right? But it'd be the same as what I wrote, but I prefer what I wrote. It's the same. Yeah. Okay, so is that above or below 1/4? Is that above or below negative 1/4? Is below? It's a trap. Is it not a trap? Let's see. Yeah, calculator. So we have, just do it. Just do it on your calculator. Whenever you get confused, do it on your calculator. Or, it's above because it's negative. That's what I was going for, yeah. So we have this number, but it's negative. We divide it by 4016. This is equal to negative 2.48. We are above 1/4 because we are negative. So here the only way I get that right is by visualizing it. And I know a negative 1/4 is down. And I am not as big in magnitude, so I am above. So f of x approaches negative 1/4 from the positive side. I know the value is negative, but I'm still on the positive side of that. I'm above it. So that's why we use the plus notation there. And as x approaches negative infinity, please just take my word for it. We approach negative 1/4 from the negative side. Okay, we could do it, but I think you got the idea. Okay, now let's do approaching our vertical asymptote. So we're going to choose values of x around negative 1/4. So as x approaches negative 4 from the positive side, I am going to test that with f at negative 3.99. All right, you can see that that's going to give me a value that's just to the right, just from the positive side of negative 4. I have to do this by visualizing, or else I make errors. Okay, so f at negative 3.99 is going to be equal to negative 3.99 minus another 4 all over negative 4 times negative 3.99. I recognize that's going to be positive, minus 16. I get this is equal to negative 7.99 over, well, what is that bottom? I don't know what the bottom is, so I'm going to evaluate the bottom. I know what it is, but I'm pretending I don't. 4 times, but it's negative, multiplied by 3.99, but it's also negative, equals that minus 16 is, I get negative 0.04. So am I going to positive infinity or negative infinity?
Positive.
In my experience, that's what happens with two negatives. They make a positive. Like, you know, like I'm a super drag and hard to be around, but so's Connor. So the fact that we have the two of us in close proximity actually makes this class tolerable for a lot of people. So thank you, Connor,
No problem. Thank
for being my comedic foil or something like that.
you. That's good.
Okay, good.
Glad to be that.
Yeah. Okay, so as we approach 4 from the positive side, we are off to positive infinity. As we approach 4 from the negative side, I would test f at, negative 4.01 or something like that. And then I would end up with this is equal to negative 8.01 over something that's in the positives. Okay, I would get 0.04, but it's positive. Okay, and negative divided by positive makes off to negative infinity. Okay, that's how you do your tests. Got questions about doing these asymptotic tests, or is it pretty straightforward now? Cool, good. All right, great. So now we graph the thing, and we graph the thing just like with our key points, put it on and stuff like that. So I'm going to use a similar scale. I'm going to draw my asymptote. So my asymptote here, my horizontal asymptote is at y is at negative 1/4. So I'm just going to set that to be negative 1/4. Okay, and then my vertical asymptote is that x is at 4, so rather than get confusing, I'm just going to do that here. X equals 4. I'm going to grab my key points, are 4, 0. X is negative 4 for my vertical asymptote. Gross. Of course it is. Negative 4, 1, 2, 3, 4. There's x is negative 4. There's my vertical asymptote. Okay. When the function is equal to 0, x was equal to 4, so I can put that on 1, 2, 3, 4. There's one of my key points. And y was equal to negative 1/4. No, y was equal to 1/4 at our y-intercept. So we're there for our y-intercept. Just getting that. I've got so many signs that are flipped in this problem. It's kind of making me go cross-eyed, but that's why checking these things carefully really helps. So now I've got these 2 points. I know my asymptotic behavior. I know I'm going down towards the asymptote that way, off to infinity from the positive side of negative 1/4, and up here towards positive infinity from the positive side of negative 4. That's negative 4, Mr. Jennings. And then down here we are flipped. So I can reflect that point through. We go through this point here. Hey, Mr. Jennings, Mr. Jennings Prime, you said something interesting. You said you could reflect this point through there. Yeah, you've noticed it by now probably that these things are like mirror, mirror image of one another. Mirror, mirror of the function. Who's the prettiest function at the junction? Here's the junction, and you just reflect them across the mirror junction to do your function. Yeah. Okay. Okay. So one more example. You can get started, though, on your delightful textbook practice, which is available on the D2L, or you have your own copy of the textbook. Go, team, go. Practice. Get ready for the test. Build your skills. Go, go, go. This is my approach of cheerleading to encourage you to do your practice so that when the test comes, you're not figuring it out that day. Figure it out today. Ask me the questions today. And then on the test, you're like, this is easy, Mr. Jennings. Why'd you give us such an easy test? I didn't. You just practiced, so it became easy. It's a little bit like saying, why is this 225-pound deadlift so easy? It's because you practiced with 315 pounds for months. And now the 225 is like, well, someone need this feather moved around the gym? Like, what are we doing? That should be your test experience. So work hard now. Go, go, do your practice. Go, go.
Do we have a count and a non-count test?
Oh, yeah.
It's not to be day after, like it's not Monday, Tuesday?
It's Monday, Tuesday.
You guys heavy with that? You guys heavy with that? You guys heavy with that?
Yeah.
Yeah, Nathan, can you lift heavy?
You lift heavy?
I thought you were a calisthenics god.
Calisthenics.
Yeah.
Why did you say that?
I didn't think you like actually went to the gym. I thought you were a home gym like.
Well, I used to.
I thought you were a home gym like exercise with your body weight type of guy. And I thought that's how you do workouts. Sorry. We talked about workouts a bit like over the winter break. That's what you're doing, right?
Yeah, that's pretty much what I do. But I
I know
also
you run a lot. You bike a lot.
put my bike away.
Yeah.
I think I told you that because my dad told me I had to because I kept crashing it over there.
Sorry, you're like pedals bike?
What do bikes usually?
Yeah, do bikes not have pedals?
I was picturing like an electric bike or something.
So electric bikes still have pedals.
Okay, you know what, whatever.
We're just more physically.
A manual bike.
A manual bike.
Like a remote control? What do you mean?
Just see that you exercise.
I exercise, I was like, use a bike. I just couldn't be bothered.
Connor, you should exercise. And all that means monkeys.
But she gets benched.
They wish they did bench me.
They wish they didn't bench you.
Was 4 over 6? 2/3.
It's tough as nails.
That didn't go hard.
We looked it up. Me and Georgia were on our team by a big gap. It's not like, okay, someone's like 8 minutes behind us. No. It's like
I probably should have gotten a couple penalties.
a goalie? What'd you do?
A lot.
Is he not
Like, and I don't really get angry on the ice.
Then what sport are you playing?
I'm a goalie.
So nothing.
More exercise. Do you mean like a pedal bike?
Dude, but you know that one city like with your hand? You said you were crashing it. You were crashing your pedal bike.
Because I was biking on ice. Because I wanted exercise.
It can happen in other ways.
But that's the way I chose to because I like biking.
Sometimes you just gotta hang it up, you know?
Skates and laps.
Weird.
See, I'm actually not a bad skater.
Aren't you supposed to
Could the
skate
following
on ice?
vehicles please be moved as soon as possible? A black Toyota pickup truck, license plate CE 85784. A green Jeep with license plate CTJJ 477. And a red Ford pickup truck, license plate AY 94923. Again, if you drive a black Toyota, a green Jeep, or a red Ford pickup truck, please move your vehicle as soon as possible.
It's not even in the police, like, locked. It's like basically like, you know how the entrance comes in like this?
Welcome to the bus, Luke.
I could see Luke driving a pickup truck.
Oh, yeah?
Someone here at this table wants to drive a
My
pickup truck.
collar's not good and my neck isn't red.
I want to. The first car I'll get is a truck.
I can see you both driving a truck. I can picture myself driving. Well, I'm actually pretty bad.
I can see you at Kia Soul.
I love Kia Soul.
You're a smart guy.
I can
You
see
know
Luke in a
my
Tesla.
favorite cars? Austin. I like those type of cars, those little wheels.
I want my. I wish I got my grandfather's house. Instead, I got. You know what I got instead? In the will? Wayne Gretzky rookie card.
That's who you got in the will? That is good. It's because you're a hockey fan.
Valued at $4,000.
You sound unimpressed. Why are you more excited?
Because I love it and I think it's great and it's awesome. But like, I want to get a car and I'm dealing with a more conundrum right now.
No, you can't get rid of
No, I'm not going to. I'm not going to. My grandfather told me to keep his insurance if things go wrong. He said, "Oh, he's like, if things go wrong, you've got the Wayne Gretzky rookie card." I think it's in Beachy too. I'm so excited to get out this summer.
What do you mean by get out?
I'm just going to be out in the world as much as possible. It's all gonna work out, right, Aaron? It's all gonna work out, right? It's only go perfect.
Let it all work out.
You know who's coming to Ottawa? Colby Seagull.
Team Ottawa? Yeah, that was bound to happen.
Why do you say that?
Cause
Did he just get off of
he acts like he wasn't there from the start. He was.
Should we pause it?
You know what I mean? Like,
I haven't talked about university. I talked to you for the first time about it today.
just he was.
Pause it or
Yeah,
negative?
he was doing a lot.
On the bottom is
Ottawa's pretty
negative.
far. He visited a lot of times. Did a lot of things with them.
So mechanical engineering.
Yeah, and I'm saying is.
But it's just one.
I
He's also thinking
calculated
about
by
ultimate.
-6 by
He's pretty sound about everything. Yeah, and he's good friends with
Shouldn't this be 3?
baseball teammates. It's our Carlton right now for engineering. So
Who's that?
Marshall Curry.
What do you get for horizontal?
I feel like I recognize him.
He's a very tall man. He's got 2 bad knees. Great swimmer. Great swimmer.
What are you asking? What are you asking?
Like he won off every year.
I thought that was your hand on main hat. Okay.
I guess as a
My line is there.
I wasn't at first.
I wrote 2 or 3. Wait, I wrote negative.
What's your?
Yeah, that's what
The
I'm
first time that I was locked in a car, I attended. Okay, you see this, it starts off really good, right? Okay.
Who is that?
That didn't have. Oh, see,